In this short video, we'll take an introductory look at activation records and the call stack. So in order to implement scope on a machine, the bindings and other runtime information need to be stored as individual units. So an activation record is the storage of all the necessary details of a single function call. It corresponds roughly to a single scope, and it includes information like parameters, local variable bindings, as well as a number of bookkeeping pieces of information like the static and dynamic links, and references to other things like where the function itself is, the body of the function, the current line that we're running, where to return when we're done, that sort of thing. So activation records contains all this information. Sometimes they're called stack frames in languages that use a call stack, where a call stack, otherwise known as the execution stack or the program stack or the control stack, sometimes just the stack, is a data structure used for activation records in most imperative programming languages. So the purpose of the call stack is to organize the process over multiple procedures. It maintains the organization between the separate activation records, which each represent individual function calls. The call stack sort of brings those individual function calls into one large structure. Right, so Scheme doesn't actually use a call stack for reasons that we'll cover later on in this chapter, but for now it makes for a familiar model of computation, so let's go over the details here, and then we'll come back to it in future videos. So first off, let's consider the example up on the screen, which is the sum of squares code that we've seen before. So the code says define sum of squares and square as we've seen them, and then run sum of squares with the values 3 and 4. So what this does when we call sum of squares, or actually before we even call sum of squares, the call stack itself has an activation record for the global and the primitive scopes. So I just draw them together here because they're sort of the top level. It doesn't really make sense to distinguish them as far as we're concerned, but they are in fact distinct, so it's good to mention that they're both there. Now in the global and primitive scope, we have storage for some of the bindings that we created. So we bound the name square and sum of squares to procedures here, so we have bindings for those. In the primitive scope, there'd also be bindings for things like the plus symbol and all those as well, but again, no sense drawing every little detail. And then what happens when we call sum of squares is we create a new activation record for this instance of that function call, and that goes on top of the call stack. So global calls sum of squares, so we have sum of squares which now has storage for its local variables, in this case the parameters x and y, with the argument values 3 and 4. Okay. Then sum of squares calls square x and square y, so we call square of 3, we get an activation record for square where x, the local variable for square, is bound to the value 3. That does its work, and then it finishes. We go back to sum of squares, and sum of squares then calls square y, where y is 4, and we get another new activation record for square where the parameter x is bound to the value 4. So it's important to note that each instance of a function call gets its own activation record, okay? So each application is its own separate entity in memory with its own storage of local variables and all these things. Now, as I mentioned, activation records contain information like all the local bindings and parameters and all that sort of thing, but also contain some bookkeeping information, chief among which, or most important as far as this course is concerned, are the dynamic and static links. So the dynamic link points to the activation record of the procedure that called the current one. It's called dynamic because this could be any procedure, so it's not known until runtime. Okay, so I'll just draw these on the left here. So the dynamic links down this side. So for example, sum of squares was called by global, so the dynamic link would go from sum of squares to global. Similarly, we called square from inside sum of squares, so for inside square, the dynamic link tells us, well, we have to go back to sum of squares when we're done. Okay, so this keeps track of who the calling procedure of the current procedure was, or more specifically, what specific activation record created the current activation record. All right, so when we're dealing with languages that use a call stack, this dynamic link will always point to the block directly below, because that's how the call stack organizes these activation records. When we make a function call from global, it gets put on top of the stack, and the dynamic link points back to the thing that did the calling. Okay, so even on a call stack, though, we still need this dynamic link because these activation records, though I've drawn them as relatively equal-sized squares, will actually require different amounts of information. For example, square only needs to store a single variable, while sum of squares needs to store 2 variables. So it needs at least twice the amount of space as far as storing parameters is concerned. So the specific address of where the start of that activation record will be on the call stack or even just anywhere in memory, that needs to be recorded so that when we're done here, we know where that activation record is and we can get that information to continue on with our process. Okay, so the dynamic link points from the current activation record, so if Square is currently running, and it points to the activation record that spawned this one or that created it. All right, on the other side, we have the static links. And static links point to the activation record of the procedure where this one was defined. So where the dynamic link points to is where it was called from, the static link points to where it was defined. So the static link points to the enclosing scope is another way of thinking about that. And this is called static because it matches the code structure, which doesn't change during runtime, right? We have lexical scoping, which means the enclosing or the nesting of scopes matches the nesting of blocks of code, like functions nested within functions. So the static link will always point to the enclosing scope, so it doesn't change in the middle of runtime. Where this thing was defined is written in the code itself. All right, so static links for square and sum of squares. These were both defined in the global scope in this example, so both of their links point to the global scope. So if we want to know where we are in, where square was defined, we go to this global scope. We want to know where sum of squares was defined, we follow the static link, and that lands in the global scope as well. Right, so the main point about the static link is that this tells us where to do our variable lookups. It gives us an idea of if we're in square, or actually a good example is if we're in sum of squares and we use a symbol like square here, which isn't defined locally, we need to find what is the meaning of that symbol. So if we don't find it locally, we need to look into the enclosing scope, and the way we keep track of where that enclosing scope is by following the static link to the enclosing scope. If square is there, then we find it. If it's not there, then we continue on down following the chain of static links. Now let's do a slightly more involved example, going back to our square root code. So this is the square root code taken straight out of the lecture notes here. So we have square root x, defining square, good enough, average, improve, and square root iteration, all those helper functions. And then square root iteration here is the body of the square root function. And then we call square root 25 in the global scope. Okay. So the call stack for this, we start with square root. So that says go to here, walk through all these, define all of these things. So we start with the global or primitive scope. It's always at the bottom of our call stack. And then when we call square root, we create an activation record for square root. And it has bindings for all of its parameters, so x at the value 25, and all of the locally defined functions. So square, good enough, and all those are all bound within the activation record of square root. Right, then square root, if we're just going to follow a line here, so square root calls, let's say, square root iteration. Square root iteration calls improve. So square root calls square root iteration eventually calls improve, improve calls average, and average is sort of a terminal call there. So that's what one pass or one step through this call stack would look like. So because square root was called from global, it's put on top of global. Because square root iteration was called from square root, it's put on top and just building up this stack here. Now, as far as the dynamic links are concerned, so the dynamic link again points to the calling procedure, which again, if we have a call stack, is always just the activation record directly below the current one. So since average was called from improve, the dynamic link points from average to improve. And again, this tells us where to go back to when we're done running this function. On the other hand, the static links, these again point to where the functions were defined. So square root was defined in the global scope up at the top here. So the static link from square root will point to global. Everything else, all the other functions in this example, are defined inside square root. So all of their static links will point to square root, where they were defined. And again, this controls the variable lookup. So if we can't find a variable locally, we follow that static link and check there. Okay, so repeating until we find either the variable we're looking for or the bottom of the stack. So for example, it's a good example here. If we are in, let's say, improve, there's a few examples here. So free variables in improve include average and x, as well as the divide symbol. So if we want to know what's the value of, let's say, divide, because well, I suppose average would happen first. Want to know what's the value for this symbol average? If we're in improve, the activation record for improve, there's nothing called average here. So we follow the static link, that brings us to square root, and sure enough, there's a function called average, so we'll use that function. Similarly, guess, we find it locally, so that's done. Divide, we don't find it in improve, so we go down to square root. There's no division function here either, so we follow the static link out of there into its enclosing scope, and we end up in the global scope, which would have another static link to the primitive scope, which at that point we would find all the primitive definitions. And similarly with x, if we're in improve, we don't find x, we go looking into the enclosing scope, and there it is, bound to 25 in square root. So the sequence of static links forms a chain known as the static chain, and this is what's used anytime we want to do some variable lookup. We start in the current activation record into the enclosing scope, enclosing scope, enclosing scope, until we either find the value we're looking for or we reach the end of the static chain. And that's it for this video. We'll return to the topic of activation records in a future video once we learn more of some of the weird stuff that Scheme can do.